So the next thing we're going to talk about is refraction. Now, refraction is probably the hardest thing for students to really understand and grasp because it deals with how light behaves, but it's really kind of weird. So what happens is when something with an energy is transmitted through something, that something it's moving through, we call it a medium. So right now, the light from the light bulbs that are above me right now, they are traveling through the air. That's the medium through which they are traveling. You can see behind me in the cabinets, they're actually reflecting. Part of the light is reflecting off the glass. Some of the other is moving through. So the glass is a medium that the light, part of it at least, is moving through. With refraction, when the light moves from one medium through, and through is the key word, through another that has a different density, then the light will slow down. And when it slows down, it will change directions. And so I've got some water, and then I have a prism, and then I have a hand lens. So we're going to kind of take each one in turn. The water, if you look at the meter stick, it's very clear that there's something not going on correctly with this meter stick, right? So it's fine. It's still in one piece. This is just sort of an optical illusion because it looks broken. But what's happening is the water is more dense than the air. So when the light moving through the air at a certain speed hits the water, it's going to slow down. And so the image becomes distorted. Now, what's interesting is, depending on your angle, it looks different. So the angle I have you set up with right now is you're seeing it almost like it's broken. Like if I stick my finger in here, then it sort of looks like it's broken. Like it looks like my finger kind of got cut off, which is sort of crazy. But if I turn it, then it no longer looks broken. It just looks bigger. It looks wider. And so similar effect, but because the angle is different, I don't see this break. Now I see I've got like a skinny piece and a wide piece. But again, same thing going on. The light is moving through the air at a certain speed. It hits the water and it changes speed. Once that change in speed happens, then the light's going to shift. It's going to change direction. It's going to bend, for lack of a better word. All right. So this is a great example of refraction. All right. Another example of refraction is with a prism. Now this is really confusing to a lot of people. I don't have a light strong enough to generate, and this prism's really not large enough to generate the effect I want to. But if you have a small prism like this and you look through it at the lights, and if you just look through it around the room, you can see it all over, but the lights, it's very pronounced. So when you look through it, you see these rainbow colors. Now, earlier in the video, when we talked about color, we talked about the fact that visible light, white light, is all those colors from the rainbow, from roids you have, just sort of all overlapping one another. Well, what the prism does is when I look through that light and the light passes through it, because of the way the prism is shaped and the material it's made of, when the light passes through it, it not only slows down, but it sort of spreads out. And so this overlapping red and orange and yellow and green and blue and indigo and violet, those overlapping waves, they sort of start to spread out a little bit. And so as they spread out, I can now see red light and green light and blue light and yellow light. And it's very, very visible to see those things because of refraction. Because when it hits the prism that's more dense than the air, it's going to shift and change directions. Now, this can be manipulated, and we do manipulate it. We use this in a lot of ways, and one of the ways in which we use it is with a magnifying glass or with a lens. Now, a lens is just a curved piece of plastic, and the curve is the important part. If the plastic was flat, if this prism was just flat, then it wouldn't have the same effect. But because of the shape, when it hits, that's what causes the bend. It's the density and the shape. All right. Now, a hand lens does some really, really cool stuff. And the reason that it does it is because when the light hits the curve, and this is a convex curve, not going to be confused with a concave curve. A convex curve is sort of the circular shape on the outside, so it's curved on the outside. Convex is it's curving in. Or, I'm sorry, concave is curving in. So if you think of cave in, it's curving in. Convex, it's curved out. So with a convex lens, when I look at something close, like if I wanted to take a look at my ring, for example, if I hold it close, it's going to enlarge that thing that I'm looking at. All right, it's going to make it bigger because when it hits, basically what it's doing is it's concentrating it so everything's kind of more packed together, so it just looks bigger. Now, what's really crazy is if I pull this back far enough, the image will get all blurry. All right. Now, I've got a graphic up right now of a convex lens, and that part that's circled, that's the part we're seeing right now, where those light rays from my ring are all overlapping. So it's just a jumbled mess. And so I can't really see anything. And if I keep pulling back a little further, now my ring is upside down. Because the light has bent so much, and the angle changed so much that it actually flipped the image over. So our eyeball, actually, works in a very similar way. We have a convex lens over our pupil. And so when the light comes in, if you look at that cross-section of the eyeball that's up there right now, when the light comes in, it will bend because of the curve and because of the change in density. It will bend, and the light beams actually change direction slightly, and it will flip or invert the image that's on the back of our eye. And our brain takes that, or our eye takes that image up to our brain through our optic nerve, and then it flips it back over, so we don't see the whole world upside down. So really, really strange, really, really weird. If you're confused by that, you're not alone. Concave lenses work a little bit differently. The way that they bend the light is very different. We don't have a lot of uses for for concave lenses. We use them in some telescopes and some things, but we use convex lenses a lot. One place where we use them both together is on eyeglass lenses. So if you wear glasses and they're prescription, if you look on the front, it'll have a curve. It'll have a convex curve. But then on the inside, it's got a concave curve. And what we've figured out how to do, what our ophthalmologists have figured out how to do, is we figured out how to manipulate those curves to make light bend just right so that people with vision problems, like myself, we can see. Now, I'm wearing my contacts right now, which is basically the same thing as an eyeglass lens. It's just shrunk down. It sits right on top of your human lens. But that contact lens bends light. It refracts light. It's an example of refraction that allows us to see. Now, refraction it's kind of crazy because it's weird to think of a beam of light hitting something and then spreading out or changing direction because it's hitting something. But if you can imagine, if you're running on concrete and then you get into sand and you start moving slower, that's what's happening to those beams of light. They're moving through the air at very high speeds, and then they hit the water, or they hit the curve of a plastic lens. And because of the change, they change. The direction changes. The speed changes slightly. So, refraction, pretty tough to kind of wrap your brain around, but if you want to go back and review, a great thing to do is go back and look at those images. See how the beam of light is hitting that medium and then changing.